Let's see example 1. Let's say you are given two rectangular conductor of surface area A, filled with a dielectric material of permittivity epsilon naught. The distance between the conductor is D and the voltage difference is V naught. Prove that the capacitance is C equal to epsilon naught A over D. So basically you are given a general expression of capacitor that you already used in other course. But how can we derive this equation? By using EMT. And from the equation, you are not given the detailed location of what variable that you need to use. It can be X component, Y component, or Z component. Okay, so you can use any, but the final answer will be the same. And here, you are not given any charge system as this inside your material, so we will be using the Laplace equations. Okay, first we have to sketch. Let's say I assume that our rectangular metal plate is placed on XY axis or parallel with XY axis. So I put one plate at Z equal to 0 and another one plate at Z equal to D. And I connect the positive V0 to the upper plate and ground to the bottom plate. And I label this one to be the positive charge as this, and this is negative charge. So the E field should be going down. Okay, this is just a label to make it easier for analysis. Alright, let's say this is B, this is A. So you have to use the Laplace equation. The Laplacian of V equal to del V square divided by del Z square equal to 0, because I put the variable is Z, so I use the Z's. Therefore, when you solve the double integration of this, you got the expression of V is equal to C1Z plus C2. And you have to solve what is a C1 and what is C2. When V equal to 0, we connect to ground, which is 0, and we put C1Z equal to 0 plus C2. So this one will become 0, and C2 also becomes 0. When Z equal to D, we connect to V0, so equal to V0, equal to C1, Z equal to D, plus C2 is 0. So you got C1 equal to V0 divided by D. So this is the general expression of potential inside your dielectric material, which is V0 over D Z volt. Next, we can find the electric field intensity by using gradients. So for the gradient, you have to differentiation of Vz. You got negative V0 over D in the direction of Z. So it's the same as what we label here. Next, we have to find what is the charge density at Z equal to D. Here it's supposedly to be the positive charge, so it's equal to Dn, or equal to epsilon naught En equal to epsilon naught E dot product with a normal component to the surface. When Z equal to D, so the normal component will be going down, which is negative Z. So when you solve this problem, you got S equal to epsilon naught V0 divided by D coulomb per meter square. When you obtain the rho S, so the capacitance equal to C equal to Q divided by VAB. Q here is basically Q at D, Z equal to D, this plate. So Q equal to rho S A. A is the surface area, divided by VAB here. The potential between this plate and this plate is basically V0, divided by V0. So you got epsilon naught V0 divided by D multiplied by A divided by V0. So V0 can be cancelled. So the final solution is C equal to epsilon naught A over D. So, proven. For example 2, basically is quite similar when we compare with example 1 because we still given a parallel conducting plane separated with the distance D. The only difference is the conducting plane is infinite in size. One of the conductor at Z equal to 0 is connected to V equal to 0 volt, which is grounded, and the other conductor at Z equal to D has V equal to V0 volt. Assume rho V equal to 0 and epsilon equal to 2 epsilon naught between the conductor. The first question is find V in the range of 0 less than Z less than D. And then electric field between the conductor, C the rho S, and D the capacitance per square meter. Basically the question is more the same except the capacitance is per square meter. So you have to divide the capacitance with the area. For the solution, right, the figure is the same except the size is A infinity. So we have the positive rho S at the top and negative rho S at the bottom. The top plate is connected to V0, the bottom plate connected to grounds. And we have a positive charge here, so that means the E will be going down. The dielectric material between two plates is epsilon equal to 2 epsilon naught, rho V equal to 0. So we have to use the Cartesian coordinate where the del square V, or this is Laplacian V equal to del V square divided by del Z square equal to 0. So the same solutions, and this is also the same when Z equal to 0, we got C2 0, Z equal to D, you got C1 equal to V0 over D. These is still the same expressions, so I go fast. For B also the same, this is the gradient. To find the E from V, you got negative V0 over D in the direction of Z. Okay, the same thing. Rho S also the same thing except our epsilon equal to 2 epsilon naught. The normal to the surface also the same, is going down, which is 2 epsilon naught negative V0 over D Z dot negative Z. You got rho S equal to 2 epsilon naught V0 over D coulomb per meter square. When at Z equal to 0, you got the negative rho S, because the normal component is going up, so it's positive Z. For D, C equal to Q divided by VAB, where Q equal to rho SA over VAB is V0. So rho S is rho S when Z equal to D, you got 2 epsilon naught V0 over D over V0. V0 can be cancelled out, and you got 2 epsilon naught A over D farad. But we want to find the capacitance per meter square, so we have to divide C over A. You got equal to 2 epsilon naught over D farad per meter square.